So, welcome to this talk about magnetoresistive position sensors, and in special we will have a look to the KMXP series here. My name is Andreas Voss. I'm a R&D product development engineer at the site in Dortmund, dealing with all kinds of magnetoresistive sensors. So, who we are. So, we are a leading company in connectivity, and we also have a large range of sensors, especially photo optics, humidity, pressure, temperature, and position sensors. And that's the section where I'm sorted in. So all these magnetic sensors are used for position detection. We are designing our sensors by ourselves, so we have the know-how, capability, how we have to design such a chip, and we are able to do the wafer process in-house. So we will guide the product until the finished wafer. After that, components are made out of these chips, so this is something which could be sold to the customer and is used widely in the position measuring range or detection of presence and so on. And last but not least, when it becomes customer specific, then special design leads to systems like shown here for level sensors or linear displacement sensors. Let's have a look in general what's behind the magnetoresistance effect. So the magnetoresistance is the property of a material to change the value of its electrical resistance when an external magnet field is applied. This was discovered first by Lord Kelvin many years ago, and basically you can think about of this like shown here. So you will have a wire and the current is flowing through this. Then if you place a magnet parallel to the current flow, the resistance is high, and if you place the magnet perpendicular to the current flow, resistance is low. So as long as you are using a magnetoresistance material like this nickel wire here, then this effect could be shown easily. So let's have a deeper look what you can do with this technique. So on one side, if we think about linear magnetic position measurement, it's thinkable that we will have a moving magnet, and if we now want to determine the position over a longer distance, a sensor array is needed. A good thing on this is that this is a scalable solution. It's an absolute position measurement. Let me say, so summarizing this is the magnet moves and we have multiple sensors. There is a second webinar dealing with this topic. You can follow this link here. Today we want to have a look to the vice versa situation, looking to what happens if we have a sensor moving over multiple magnets. So when I talk about multiple magnets, we call this magnetic scales. It's basically an elastomer filled with ferrite particles and magnetized in a certain pattern. We will have a steel back on the back side, which ensures a good handling and safe assembly. Typically, the width of these bands is 10 millimeters. This is a industry standard, but there are varieties from 2 to 20. Normally it's delivered in rolls. Typical number is 50 meters, but there are also rolls up to 100, 200 meters if you have to discover a longer range. So these measurement tasks need a special kind of sensor, and this special kind of sensor is called KMXP. So, and I will now give you a deeper view inside this kind of sensor. So The magnetic situation over such a scale is shown here on the left side. You see the magnetic field vectors. They are turning for 180 degree at a distance of 1 pole length. The magnetic field varies with air gap between the scale surface, and if you go up, and therefore you see here an illustration of the magnetic field strength, and you need to know that all these sensors work until a certain amount of field strength. If the field strength drops under the certain number, then the so-called strong field situation is no more given, and therefore the sensor needs to place near to the scale. So on the left side, a more detailed look to the vector field distribution over 1 pole pitch. So this is the design pole pitch for the system, for example 5 millimeters, and you see there is a 180 degree field angle turn for this 1 pole pitch. That is important to know because now if we go a bit deeper how the sensor works in detail, we need to know this. So AMR sensors, as I showed in how Lord Kelvin discovered this, these sensors are measuring basically the field angle, not the field strength. And that's the reason why this 180 degree turning for each pole is ideal for the AMR technology. The sensor itself is built up with a gradient principle. That means the sensor detects local field distributions, but it's stable against homogeneous to disturbing fields. That's a great advantage. Internally, the sensor is built up out of 2 whetstone bridges, and if such a sensor is moved for a distance of 1 pole pitch, the output signal of the both whetstone bridges show a sinusoidal signal, but the sensor is designed in that way that we have a 90 degree phase shift, and the output will be then a sinus and a cosinus. There are commercially available interpolators which do the calculation, which is shown here on the left upper side, but this algorithm could also be implemented into microcontrollers. Very important fact, sensor and scale have to match. That means if we have a pole pitch of 2 millimeters, for example, we have to use a sensor which is addicted for a 2 millimeter pole pitch. So if we have a look to the output of the 2 sensor bridges, and we take an example of a KMXP 1000, which is dedicated to a pole pitch of 1 millimeter, then you see here traveling the sensor for 1 millimeter gives you a full period of the sine and cosine signals. And another point here is that happens even for different air gaps between sensor and scale. So here is a curve shown, or here are some curves shown for air gaps of 0.1, 0.3 and 0.5 millimeters. And there is no big difference in the signal. That's very good. So this sensor can deal with variations of the air gap. So as I said already, we have dedicated sensors for a fixed pole pitch. So this is what needs to be known. There are 3 standard pole pitches in the market, 1, 2 and 5 millimeter. And for these standard pole pitches we offer a certain sensor version. So and that's found easily in the number ring of the sensor KMXP 1, 2 and 5000. So what's the difference between these models? So let's start with the 5000 version. So it's addicted to a pole pitch of 5 millimeter. it's designed in a way that the sensor surface is scanning or is long enough to scan the field of one pole. So that means with that sensor, it's possible to have a wide air gap. The rule of thumb is half of the pole pitch, and yeah, the resistance is low, so it's dedicated for normal industrial applications where higher air gaps are demanded, but the accuracy is yeah, moderate in yeah, if you compare it to the other versions, which I will show now. So the KMXP 1000, for example, it's integrating the field of 4 poles at one time. Here we need a smaller air gap. As I said, the rule of thumb is half of the pole pitch. That means the maximum air gap here is 0.5 millimeter. But this sensor can do very accurate measurings as the accuracy scales with the pole pitch. And another benefit of this sensor is a higher sensor resistance, which makes it interesting for battery-powered applications. So yeah, we have smaller pole pitches. That means we have a better accuracy, but also the air gap could not be so big. Bigger pole pitches means we can do a wider air gap, but the accuracy drops. And the best out of two worlds is the KMXP 2000, which is in the middle. So we can have a maximum air gap of 1 millimeter, but we can also achieve accuracies near to the accuracy of the KMXP 1000. So now let's have a look what are the benefits having these sensors in a DFN package. In former times, such sensors were built up with the chip-on-board technology, but there are some hints with that, especially it's not a standard process. That means building up sensors in that way is very costly. That is solved with a DFN package. Yeah, we have a traceability now. We can place a date code on it. And the very big benefit is that all these components are pre-tested for the bond connection. So if you think about assembly on the PCB, the common way assembling this was the flat assembly shown on the left side. This was the only way which could be solved by the COB technology also. But as we now have a DFN package, it's also possible to assemble this sensor in a perpendicular way, which is a big benefit for compact applications where we are faced with room restrictions and therefore systems could be built very small. This could also only be solved with COB with DFN packages. Now let's have a look to the performance. A simple example here, KMXP 2000 together with an sinus cosinus interpolator from IC House. We choose a 1 micrometer resolution of the AB quadrature signal of this interpolator, and this measurement showed an accuracy of plus minus 2 micrometers. Yeah, you see it's a very compact size of the PCBA, and one benefit of this interpolator is that it's also addicted for high speed applications. MR sensors react very fast, so yeah, for fast turning motors or if you have XYZ stages which have to move very fast, and whereas an accurate measurement is asked, this sensor is optimal for this application. Let's have a small summary of what I've taught so far. So we have a rule of thumb for the accuracy, that's 1% of the pole pitch, and the rule of thumb for resolution is 0.1% of the pole pitch, and as I already mentioned, if we think about air gap, then the rule of thumb is half the pole pitch. As we do have a non-contact principle here, this application is perfect for harsh environments. Think about oil and dust. The magnetic measurement principle doesn't care about this. Here in these applications, optical sensors have their problems, and that's why these measurement tasks are often solved by magnetic sensors. Yeah, we can achieve a very precise and high resolution measurements. And a very big benefit is that we are insensitive to external fields due to the gradient principle we use inside. So let's have a look how it works. If you want to do a linear measurement, then the sensor scans a magnetic scale, and shown here is, for example, a 5mm based pole pitch. That means we have a 180-degree field angle change for one pole pitch, and this is plotted here. And for each pole, the sensor could measure the field angle change. So if you now want to establish a measurement for a longer range, the interpolation chip or the MCU algorithm needs to count the number of poles and then later on fit this together with the high accurate information within one pole. That's the way it works in interpolation circuits. But the point is, if you lose power in these systems, you lose the information where you are. That means you need a reference drive back to a reference point and then move again to the position where you want to go. That could be solved if you think about using an absolute system, that's also called Vernier-based system, similar to calipers, to the principle which is used in calipers. So here we have a two-track scale. The difference is that one track has one pole more than the other track, and if you now scan these tracks with the dedicated sensors and plot the angle signal, you see there is a phase shift. And based on this phase shift, an absolute position could be calculated even when the sensor is placed at a certain position and it's powered on. You do not need to make a reference drive. If you think about absolute positioning systems which cover very long distances, because the Vernier system is limited to, let me say, 150 millimeter, and if you want to cover longer distances, then we need to think about coded systems. So that means we will have one track incremental coded, so used as explained before, and the second track which implements a pseudo-random code. And to scan this pseudo-random code, usually a Hall array is used to determine the pseudo-random code, and to each raw pole position a certain code is addicted. So it's easy to find out the position even over longer distances with that application. So another application is pole wheel application, very interesting for MR, because MR measures the field direction and not the field strength. And if you see here, if in these applications you will have uncertainties in mounting the ring, for example, so you will have differences while turning this wheel in the field strength, but you do not have differences in the field direction. That means this is ideal, that this application is ideal to be solved by MR sensors. MR in this kind is very robust, and that's the reason why many people trust their lives on MR sensors, because this principle is used in the ABS system, for example. So let's have a look to other different examples where these techniques are used. So everywhere where you have the demand of high precision in dirt and harsh environments, I would say. So if you think about medical, syringe pumps, medical tables and chairs, where you need to have exact positions, prosthesis, surgical robots. So here you will find MR sensors doing measurement with sensor and scale together. Industrial, we have a wide application range, starting with machine tools, wood cutting machines, XYZ tables. Very interesting application is elevators, as I have shown the pseudo-random coded based systems. These are used in elevators to cover hundreds of meters for an absolute measurement. So how to find a good design? That's always the question for an engineer, and yeah, we have to find the optimum of performance, price, and the right fit to the application, and therefore we think about this application triangle where you have to count all parts of the application into another, and where you have to think about how these three corners are playing together. So if you think about the sensor and the magnet, how does it work together, then we have to think about which pitch would we use, which magnetization technique is used for the scale, which air gap are we allowed to. So does our application needs a bigger air gap, then we need to go to bigger pole pitches, for example. We need to think about how to integrate the sensing magnet to the application. So is there enough space to glue the scale? Or should we do it vice versa, that we will set the sensor to the application and glue the scale to a different part of the machine? And the same question for the sensor. So that's as you need to place both of it into the application, that will be the same question for this path here also. We are often faced with restricted geometric situations, so that means miniaturization is a big topic, and as I shown, the perpendicular alignment of the sensor is a good solution to go very compact with these applications. So let's come to a conclusion. If we think about incremental measurement, a single track is enough together with one sensor. If you think about absolute measurement, then we will have the possibility to do it with a dual track non-use, which I showed. There's also a concept to have a single track scale, which also is coded in a non-use way. That's a very special application for room restricted applications. And yeah, if you need longer distances, for example, in the elevator situation, then the dual track with digital code will be a solution for that. So we have talked about the sensor moves over multiple magnets. That is one way to solve the measurement task. The other way around, when the magnet moves and we will have multiple sensors, is covered by a different webinar. We have here a different application field. For example, level measurement is this version is heavily used. Here the accuracy demands are not so high, but it's very important that we will have a light magnet, and there the sensor cannot move in this application. There the magnet needs to be moved. And if you think about applications, what we talked in this webinar, their accuracy is the big demand. So I would say these scale-based systems, they are the sensor of choice if a high accuracy is demanded. So thank you for your attention. You can contact us when you have questions to the sensor, and we will be happy if you would use the sensors in your upcoming applications.